All right, welcome everyone. Today, we're going to continue our discussion about integrating powers of sine and cosine. And yesterday we looked at what we do when at least one of the exponents is odd. Today we're going to see what happens when both of the exponents, both of our powers are even. And so our strategy for how to do this is we're going to break up our function into multiples of sine squared and cosine squared. We're going to apply some half-angle trig identities, which we'll read through in just a second. And that'll give us this kind of big, long expression, which we have to multiply everything out. And then when we multiply out trig terms, a lot of times what happens is that kind of bumps our exponents on the trig functions back up a little bit. So we usually have to repeat some of our half-angle trig identities. And we keep doing that until eventually we get our expression, our function, down to one of our k-form integrals. So let's first read through the half-angle trig identities that we're going to be using, and then we'll just recall our k-form integrals that are going to be kind of helpful to remember here. So first, we have this one trig identity that says what sine squared of theta is equal to. It's 1/2 times 1 minus cosine of 2 theta. Then we have a similar one for cosine squared. So cosine squared theta is equal to 1/2 times 1 plus cosine 2 theta. And so the way I kind of remember these is both of these trig identities involve a cosine 2 theta. And when the cosine terms match, we have a plus sign. If the trig functions are opposite, then we have a minus sign. You might just memorize these. That's how I memorize these. And these are going to be helpful to have memorized. One other one that we may use from time to time, probably won't use it too much, but it's related to these, is sine theta times cosine theta is equal to 1/2 times sine of 2 theta. So that's another one that we may use, might be helpful to kind of remember, at least is out there, to have at our disposal. All right, so these are the half-angle trig identities that we're going to be using for these even powers. And why are they helpful? Well, they take this even exponent. So on the left here, we have an even exponent, which is a power of 2. And by some trig magic here, it converts it into a trig function that has an exponent of 1. And exponents of 1 are going to be a lot easier to integrate versus these higher power functions. So, why these trig identities are helpful is on the left, it takes higher powers and it reduces them into lower powers of sine and cosine. And same thing for the one down here. Here we have two trig functions, sine of theta times cosine theta, and it reduces it into just one trig function with an exponent of 1. So that's why these trig identities are going to be helpful, because it takes these higher powers and it reduces them into lower powers. All right, so now we're seeing something here, cosine of 2 theta, sine of 2 theta. These things are going to show up. And it's helpful to remember our k-form integrals, because we're going to be using these quite a bit. All right, so what were they? And we've mentioned these before. But this would be things like integral of sine of kx dx, where k is a constant. Integral of cosine of kx, where k is a constant. And how we handle these is we integrate the trig part just like we normally would, Really, these are u substitution, but we probably just have these memorized. So we integrate the trig part like we normally would. So the antiderivative of sine is negative cosine. We keep our inner function the same, so we're going to keep the kx the same. And then we take that constant in front of the x, the k, and we flip it and put it in front of our trig function. So in this case, the integral of sine of kx is negative 1 over k times cosine kx, plus our c term there. What's the antiderivative of cosine of kx? Well, antiderivative of cosine is sine. We keep our inner function the same, and then we flip that constant that's in front of the x to get 1 over k in front. And so there we go. We end up with the integral of cosine of kx is 1 over k times sine of kx. And a lot of the time, that k we're going to see is going to be a multiple of 2. So it's going to be things like 2, 4, 8, maybe a 6 in there, who knows. But, this works in general doesn't have to be a multiple of 2. So these k-form integrals are going to be very helpful to remember. All right, let's try one out. Let's try one of these examples out. So let's look at example 4. We're going to integrate sine squared, and we're going to do a definite integral. Why not? And it'll be the integral from 0 to pi over 2. All right, so let's give this one a shot. And when we look at this, we have an even power of sine. So we're going to have to use one of those trig identities that we just discussed. And let's do it. Let's use, which one should we use? Well, we had a nice half angle formula that told us what sine squared of theta is. It's equal to 1/2 times 1 minus cosine of 2 theta. And we know both of those half angle trig identities involve cosine. We're doing something involving a sine, so the way I remember it is just when they're opposite, I put a minus in there. That's how I remember the formula. Now, in terms of actually working with this, we can leave the 1/2 factored. Sometimes it's helpful to just have it distributed. So another way to think of this trig identity is just to have that 1/2 distributed. Either way you want to do it is fine. I'm going to use it with the distributed version here. So when I put this in, we haven't done any integration yet. We're just applying that trig identity, and we're going to take this sine squared x, and it's going to become 1/2 minus 1/2 cosine of 2x. So all we're doing there is the trig identity. All right, now what we've done is we've taken it with this exponent of 2, and we've reduced the power now, so it's just one of our k-form integrals. So everything over here we should be able to do the antiderivative of. So let's do it. So what's the antiderivative of this constant term 1/2? That's this loose term. Well, it's 1/2 x. What's the integral of this cosine of 2x? Well, we're going to have that minus 1/2 that's in front already, so that's going to stay in front. And let's figure out the antiderivative of that cosine 2x. So that's one of our k-form integrals, so it's just helpful. Let's write it out again. So what was that formula? Well, we integrate the cosine function just like we normally would, so it's going to be sine of 2x. And then we take that constant that's in front of the x, we flip it, put it in front. So 1/2 of sine of 2x. And so that's what we end up with down here, 1/2 sine of 2x. Now we're doing a definite integral, so we don't have to worry about the plus c, because if we did include it, that's okay. It would just end up getting canceled out anyways. So we don't need to worry about that for a definite integral. We have our antiderivative. So now we just evaluate from x equals 0 to x equals pi over 2. And there we go. We're ready to go on. We have our antiderivative now. Maybe the only thing we do before we actually evaluate is just to simplify as much as we can. So the negative 1/2 and the 1/2 here, just multiply those together. Sometimes it's helpful to just simplify as much as you can before you go on and do the evaluation. All right, so let's plug the pi over 2 in. When we plug it into this first piece, we get pi over 4. Then we have minus 1/4. And then when we plug the pi over 2 into the sine of 2x, we get sine of pi. That's what we get when we plug our top number in. Then we subtract, and then we're going to plug in our lower limit, our 0. So now let's take 0 and plug it into this antiderivative. So when we plug it into that first term, we get 0. And when we plug it into that second term, we get minus 1/4 sine of 0. And we're going to be seeing these types of values quite a bit. So it's a good idea to start working on memorizing them. So things like sine of pi, you're probably going to have that memorized at some point. You should know that it's going to be equal to 0. Same thing, sine of 0, that's going to be 0 as well. So there's a lot of these important angles where you probably should just have it memorized. So 0 and pi are two of those angles. So this is going to be gone, and then everything over here is going to be gone. And so when all the dust settles, we're left with pi over 4 as the value of this integral. All right, so yeah, the main important thing here is just this first step where we use this trig identity, this half-angle trig identity, to take this higher power sine term and convert it into a lower power cosine term. And then we were able to go from there. Let's try another one. Just comes with practice. So let's try another one of these. Let's look at example 5. We're going to look at sine squared of x times cosine squared of x. And this, if we look at these, everything here is even powers. And what we're going to do is, again, we're just going to apply our half-angle formulas. So we have a sine squared. So let's rewrite that as a half-angle formula. So it'll be 1/2 times 1 minus cosine of 2 theta, or 2x rather. X is our variable here. So, again, the sine squared here is becoming this over here. And we're converting a sine. We know all of our half-angle identities involve a cosine, so those are opposite trig functions, so I remember to put in the minus there. And then we also have this cosine squared term. So it's a very similar looking trig identity, but it's going to be a plus in the middle. So for our cosine squared, that will become 1/2 times 1 plus cosine of 2x. So it'll be plus there. So that's the idea, is basically we're going to have a whole bunch of even powers of sine and cosine and just go through and convert them all using these half-angle identities. Now, where things become a little more difficult is now we have all this multiplication, and we actually have to go through and do the multiplication. So let's work it out. And we have a 1/2 and a 1/2 here. So it'll help to just get those outside of the integral, multiply them together, get them outside. So we'll move them, combine them into a 1/4 and get it out in front. Now, let's see what happens when we multiply those 1 minus cosine 2x and the 1 plus cosine 2x. Let's see what happens when we multiply those out. And we'll just do this off to the side here. And when you do this multiplication, you know, there's different ways to remember how to multiply things out. You know, you might remember it as like a FOIL type acronym, but however you do it is fine. So let's just kind of go through. And we start with the first term here, and we're going to distribute that to the 1 in the second term, and then to that cosine 2x in this, also in the second term. So when we do that, we get 1 plus cosine 2x. And then we're going to go to our next term, the negative cosine 2x, and we're going to distribute that to everything in the second. So when we take that negative cosine 2x and multiply it with that positive 1, we end up with a negative cosine 2x. And then when we take that negative cosine 2x and multiply it with the positive cosine 2x, a lot of trig functions. We end up with negative cosine squared of 2x, and we're going to have to do something with that eventually because the power has gone back up. So, but we'll get there. So the way this is set up, we get a little bit of canceling. So you might remember this when the expressions look the same and the difference is just a minus and a plus there in the middle, you do get a bit of canceling. So the cosine 2x here cancels with the minus cosine 2x here. And so we end up with just a 1 minus cosine squared of 2x. All right, so that's looking better, but we still have another even power. So we have to go through it again. So we have to use another one of our half angle identities. So we used our half angle identities here. And we multiplied everything out. That gave us an even power. So now we have to do it again. And we're just going to replace this cosine squared of 2x with our half angle formula. So let's write it out. So what is cosine squared of 2x going to be? Well, we know it's going to be 1/2 times 1 plus cosine. And what happens is we double the angle that's there. So if we go back to our trig identity, where was it? Right here, cosine squared of theta. What happens is we take that entire angle and it gets doubled. So it becomes 2 times that angle. So over here, we're going to take this entire angle here, the 2x, and we're going to double that. So it'll be 4x. So it goes from a 2x up to a 4x. And let's fill that in. And let's distribute that 1/2 now. So we'll end up with 1/2 plus 1/2 cosine of 4x dx. Okay. So we just distribute that 1/2 through. Now we're in a position where we can actually kind of simplify our function a little bit. But when looking at this, we can see we're on the right track because we started off with 2 even powers of sine and cosine, did the half angle identity once, that brought us down to just a cosine squared, did the half angle again, and now we're at one of our cosine k forms here. So we're going to be able to integrate this. But let's actually simplify it down just to make the integration a little bit easier. So when we do that, we're going to distribute the minus here. So 1 minus 1/2 is going to be positive 1/2. And then we end up with minus 1/2 cosine of 4x. And then, it doesn't hurt. Let's factor out the 1/2 and we'll multiply it with the 1/4 in front. So that'll give us 1/8 times 1 minus cosine of 4x. All right, so that's looking pretty good. Now we can actually do the antiderivative. So what's the antiderivative of 1? It's x. And then what's the antiderivative of cosine 4x? Well, this is one of our k-form integrals, so the antiderivative of cosine is sine. And we keep the inner function the same, so it's going to stay 4x. And then we take that constant that's in front of our x and we flip it and put it in front of the sine term there. And this is an indefinite integral, so the only thing we want to remember is our plus c at the end there. And there we go. We have our antiderivative. So we had to do a little bit more work there. We had to use the half angle identities a couple different times, but we got there. And maybe the only thing, if you wanted to, you could distribute this 1/8, but we'll stop there. That's fine. So that's really the idea. Let's look at one more example, example 6, and we're going to see, we won't finish this one. We'll just kind of set it up because it's going to be very similar. The work will be very similar to example 5. But here, everything, we had just these copies of sine squared and cosine squared, so we could jump right to our half angle identities. In example 6, there's going to be kind of one extra little step there at the beginning. So in example 6, we have sine raised to the power 4. So in order to use our half angle identities, it would help if I could spell that right. So what is the one for sine squared? It's sine squared of x equal to 1/2 1 minus cosine of 2x. So in order to use that half angle identity, it has to be a squared. Same thing if we had a cosine. It has to be cosine squared in order to use these half angle identities. So right now we have it as sine of x raised to the power 4. So the only extra step here is just if we have these higher powers, these higher even powers here, just break them up into multiples of sine squared and cosine squared. We're not going to have to worry about cosine squared here because there are no higher powers of cosine here. But if there were, then we would break it up into multiples of cosine squared. But we're going to do that for this sine term. So instead of thinking of sine of x raised to the power 4, let's break that up and we'll think of it as sine squared x times sine squared x. If this was sine raised to the power 6, well, then it would be sine squared times sine squared times sine squared. So you just do it as many times as you need to. So if we go back to our strategy really quick, that was this first step. So we didn't have to do it in our earlier examples, but sometimes you might have to break up the function into multiples of sine squared and cosine squared. Once you get them all in the sine squareds and cosine squareds, then you can do half angle identities as much as you want, multiply things out as you need to, and then repeat if you have to do any more half angle identities. So in example 6 here, we have sine squared times sine squared. Now we can just use this half angle formula. And so we can rewrite this as the integral of 1/2 times 1 minus cosine of 2x times 1/2 times 1 minus cosine of 2x. So we've just repeated it for each of these sine squared terms. And then just like in example 5, we're not going to finish this, but you would multiply everything out, use the half angle identity again, and keep going from there. So the rest of this is going to be pretty similar to what we did in example 5. So I'll leave it up to you to kind of fill in the details here for how to proceed further. All right, so that is really how we handle even powers of sine and cosine. Now, one kind of extra thing that extra tool that will be helpful, I guess, is sometimes we'll have powers of sine and cosine where the angles are actually different. And so just to be aware that these exist, you probably won't have these memorized, and that's okay. Are these more trig identities? So just more and more trig identities. For memorization, I would probably recommend sine squared plus cosine squared is equal to 1, and then also have those half angle identities memorized. These ones, just be aware that they exist. So what do they say? Well, they tell us what we can do if the angles in our sine and our cosines are different. So here we have sine of some angle A times cosine of some other angle B, and it's equal to, what is that, 1/2 times sine of angle A minus B plus sine of A plus B. And then we have similar ones for, sine of some angle A times sine of some angle B. It's 1/2 times cosine of A minus B minus cosine of A plus B. And then, what happens if we have all, cosines, but they have different angles? So cosine of A times cosine of B, well, 1/2 times cosine of A minus B plus cosine of A plus B. So, a little bit lengthier. If the angles are the same, well, then these just become our half. So if A and B are actually equal to each other, then these formulas just become our half angle trig identities. All right, so let's try an example just to see how we would use these. So let's try example 7. And this is really the setup where you'd want to use one of those trig identities. Is when we look at this, we have a sine term times a cosine term, but their angles are different. So here we have a 3x, here we have a 7x. So we want to use our different angle formulas. So what was the formula for sine of A times cosine of B? And I already forgot it, so let's go back. Here we go. So sine of some angle times cosine of some angle, it's 1/2 sine of A minus B plus sine of A plus B. Just be aware that these exist. They're out there. Know where you can look them up, essentially. Oh boy, I already forgot it. Plus. I'm going to make sure we get these right. There we go. All right. Now we're in shape. So we have sine of some angle times cosine of some angle, and let's just apply the formula here. So this is going to be equal to the integral of 1/2, and let's put that 1/2 right in front of the integration. So it'll be sine of 3x minus 7x. So we take the angle from our sine term and take the angle from our cosine term and subtract. So that's what's happening here. We take the angle A minus the angle B, and that's what we're plugging into the first one. And then we have plus sine of, and then we take our angles and we add them together. You know what? I don't trust myself. Yeah, okay. We're good. All right, so there we go. So we have our, we've applied this trig identity. Let's simplify now. So we have 1/2 sine of negative 4x, so 3x minus 7x is minus 4x, plus sine of 10x. And it's important to remember, it feels, especially when you start doing these and you're doing all these trig identities and the powers are going down, it feels like you're doing integration. But so far, up until this point, we've only done trig identities. So you need to remember, at some point, you actually have to do the antiderivative. And now we're in a position where we can do that. We can use our K-form. These are just K-form integrals now. So I told you these would be important. So we're going to, what's the integral of sine of kx dx, where k is just a constant? Well, the antiderivative of sine is negative cosine. We keep the inner function the same, so it's going to stay kx. And then we take that constant multiple, flip it, put it in front. All right, so let's do that. So we have the 1/2 in front. Let's find the antiderivative of the sine term here. So it's going to be negative cosine of negative 4x. We take that constant in front of the x, that negative 4, and we flip it and put it in front. So it'll just be a negative 1/4. And then we go, and we're going to do the antiderivative of sine of 10x. So we know this antiderivative is going to be negative cosine. We keep the inner function the same, so it's going to stay 10x. And then we take that constant in front of the x, where we take that constant 10, flip it, put it in front of the cosine. And there we go. We have our antiderivative now. And maybe the only thing we do is, let's just simplify this a little bit. So the double negative here is going to become positive. We could distribute the 1/2 if we wanted to. So this will be positive 1/4. Let's distribute the 1/2. So we end up with 1/8 times cosine of negative 4x, and then minus 1/20 times cosine of 10x plus c. And if we wanted to, cosine is an even function, so we could actually simplify this cosine of negative 4x a little bit further, but you know what, that's fine. We'll stop there. So we have our antiderivative now all in terms of x. So we're good. All right, so that really does it. That covers all the different kind of scenarios we're going to see involving these trig integrals involving powers of sine and cosine, or maybe sometimes powers of sine and cosine with slightly different angles. So next time, we're going to look at how to integrate more trig integrals, this time involving secant, powers of secant, and powers of tangent. So we'll see that next time. All right, so we'll see you then. Bye-bye.